Now we see the difference between the stationary and non-stationary random process. This is random processes because we have two stationary and non-stationary random processes. So based on the statistical properties of the process, we can classify the random process into two different type of random process. One is the stationary random process and non-stationary random process. So if the statistical properties of the random process are not varying with time, then it is said to be a stationary random process. Otherwise, it is a non-stationary random process. Okay. Let x of t is a random process, and we observe the random process at t equivalent to t1. Then the random variable that we obtained is x of t1. So if you know this random variable, from this we can obtain expectation of x of t1. So this can be denoted as mx of t1. So in order to evaluate the mean value of the random process, we need to have fx of t1 of x1. So this is called marginal probability density function. This is the probability density function of the random variable x of t1. Actually, the random process is characterized by the joint probability density function. So this can be considered as the marginal probability density function. So if the statistical properties are not varying with time, that indicates the density function of the random process is same. That is, if you shift this, there will not be any change in it. Follow this? Here, the distribution function is shifted by an interval t. First we are observing the random process at t equivalent to t1 and we obtain this. Now, after some delay at t1 plus t, again observe the random process. Then you will get x of t1 plus t. Okay, this can be considered as t2, is it? This is t2. So x of t2. Then expectation will be expectation of x of t2. So this is mx of t2. So here you can also write this as fx of x1. You let this as x2 because we are letting x of t2, the value that taken by this random variable is x2. So this can also be written as fx of x1 comma x2 and t1 comma t2. So what this indicates? So this is the joint density function. Otherwise you can also write, because there is no use, instead of writing fxx, better to avoid it as, or simply write as fx of x1 x2 t1 t2. That is, we combine these two. This is the marginal density, this is the marginal density. Okay, this is x of x1 comma x2 t1 comma t2. This can be considered as the joint density function. Here we obtain two different random variables by observing the random process at two different time instants, t1 and t2. If you consider this, the probability density function of this random variable is equivalent to the probability density function of the second random variable. So obviously this mx of t1 will be equivalent to mx of t2. Is that right? So in general, we can write it as x of t is a random variable and the corresponding expectation is which is equivalent to mx of t. Now obtain another random variable, that is x of t plus t, and the corresponding expectation is x of t plus t, and this is equivalent to mx of t plus t. So if these two are equal, what that indicates? That is, if the probability density function is not varying with the shift in time, definitely the expectation of x of t and expectation of x of t plus t is same. So therefore these two will be equivalent to same. Is it? That is, the mean value of the random process is not varying with time. The mean value of the random process is not varying with time, then the mean value of the random process is constant. So here you can say that this mx of t is equivalent to mx of t plus t, so which can be called as simply mx, where this mx is a constant. So if the statistical properties are not varying, what are the statistical properties? Distribution, density are the statistical properties. Therefore, the random process is said to be a stationary random process. In this case, it is called as the first order stationary process. Why first order stationary? Here, the density function that we considered is called as the first order density. That is, we are assuming its properties are not varying with time, and we observe the process at t1. Then the marginal density fx of t1 of x1 is the density function of the one random variable x of t1. So that's why this particular density function is called as the first order density function, a density function of order 1. So therefore, here the density function of order 1 is not varying with time, because this condition is satisfied. So therefore, the random process is said to be first order stationary random process. So now we consider, so again let the same process x of t. So we are observing the process at t1 and t2 and obtain the two random variables x of t1 and x of t2. Let x1 comma x2. Is it? So here we are letting x1 is the value that taken by the random variable x of t1, x2 is the values that are taken by the random variable x of t2. So therefore, fx of t1, x of t2, x1, x2. So if this is equivalent to fx of t1 plus some constant t, x of t2 plus t of x1 comma x2. That is the joint density function. Here this density function is called as the second order density function. So if you consider only fx of t1 of x1 as in the previous case, this is called the first order density function. So this is called the second order density function. That is, the number of random variables are increasing, x of t1, x of t. So this is called the second order joint probability density function, or simply second order density function of the random process x of t. So if you shift this, if t1 and t2 both are shifted by the same amount, then there will not be any change in the density function. That is, the statistical properties of this particular process are not varying with time, then the random process again is said to be stationary random process, and this is the second order stationary. So here, as we consider the joint density function, so we can write this Rxx of T1 comma T2 is equivalent to expectation of x of T1 into x of T2. Here, if you let this Rxx of T1 comma, so if you let T2 is equivalent to some T1 plus T, okay. Otherwise let this is T, so T2 plus T. This is equivalent to expectation of x of T1 plus T and x of T2 plus T. So this can be written as integral minus infinity to plus infinity. So integral minus infinity to plus infinity fx of T1, okay, and I am writing it as x1, x2. x1 is equal, this is, let this as x1, this as x2. For simplicity, I am eliminating the T1, T2. fx of x1, x2, this is x1 comma x2. Here what you will get? dx1, dx2. Is it right? See, what is the expectation of xy? Expectation of xy can be written as minus infinity to plus infinity xy, yeah, here x1 into x2. Understood that? Now, what about this? The second equation. This is minus infinity to plus infinity, and this is minus infinity to plus infinity. So this here we will get x1, x2. This is fx1. Actually, it is T1 plus T. So let this as 1 plus T. Two plus T. I am eliminating the T, okay, and this is x1, x2, dx1, dx. Is it clear to you? Don't get confused. Instead of writing, actually it is the subscript. Actually, we have to write it as x of T1 plus T, T2 plus T. Instead of writing T1 plus T, I am simply writing 1 plus T and 2 plus T. Okay, otherwise, you can write x of T1 plus T, x of T2 plus T. If you are confusing. Okay. Follow? Otherwise, T1 plus T, and this is T2 plus x1, x2, dx1, dx. Now, we already know that we are letting the statistical properties, that is, the second order density function is not varying with time. Then, this density function is equivalent to this density function. Then, this will be equivalent to this. So, therefore, the random process, that is the autocorrelation function, is also not varying with time. So, it is not varying with time, it is not a function of time. Follow? So if it is not varying with time, then we can directly represent this as Rxx of tau. That is, if you let the difference between these two is equivalent to tau, and as the autocorrelation function is not varying with time, obviously, see, if this condition is satisfied, this will be equivalent to this, is it? Because this can be replaced with this, so both are same. Then the autocorrelation function is not varying with time. If the autocorrelation function is not varying with time, then it is not a function of time. So therefore, we can write it as Rxx of tau, where tau is the time difference or time lag between T1 and T2. In the case of first order stationary, the mean value is constant. The mean value is not varying with time, then it is said to be constant. Here, the autocorrelation function is also not varying with time. So therefore, autocorrelation function is not a function of time. So it is function of only the time delay between the two times at which we observe the random process. So therefore, Rxx of T1 comma T2 can be represented as Rxx of tau. That is, T1 comma T2 can be represented as this. Okay. Because it is not depending on these time values. It is depending only on the time difference between these two times. Okay. Then the random process is said to be second order stationary random process, okay, or stationary random process. Let x of t is the random process, and we observe the process at t1, t2 and so on, some tn, and obtain the random variables x of t1, x of t2 and so on, x of tn. Then this fx of t1, x of tn of x1, xn is the joint probability density function of all these random variables. So this is called the nth order joint probability density function. So nth order probability density function of all these random variables. It is a joint density because all the random variables are jointly distributed because they belongs to the same process. So if this is equivalent to fx of t1 plus some t and so on, else we are shifting the time by some constant amount. So if this condition is satisfied, then the statistical properties of the random process are said to be not varying with time. Then the process is said to be nth order stationary process, and this is also called as strict sense stationary process. See, we are discussing about the stationary process. So here we have, based on order of the density function that we consider, we have first order stationary, second order stationary and nth order stationary process. So this nth order stationary random process is also called as strict sense stationary random process. Okay. So this is the nth order stationary. So if this condition is satisfied, it is strict sense stationary. Why? Because so all the statistical properties all the statistical measures like mean, variance, covariance, correlation, autocovariance, all these are not varying with time. They are not depending on the time. So therefore, the random process is said to be strict sense stationary random process. Sense stationary random process. In most of the practical purposes, we assume the random process or stationary random process, because the random process is not stationary. The analysis of such process is somewhat difficult. Okay. So that's why in most of the real-time problems, we assume the random process is stationary in some sense. There is another one, that is WSS process. That is wide sense stationary process. Wide sense, this is strict sense stationary random process, and there is another random process called as wide sense stationary random process. This is also called as weakly stationary random process. So a random process x of t is said to be wide sense stationary random process if the mean value of the process is equivalent to constant and the autocorrelation function of the process is equivalent to Rxx of tau. And the Kxx of tau is also equivalent to Kxx of t1 comma. So here this is very clear. The mean value of the random process is constant. It is not depending on the time. Then and this is one condition. The second condition is the autocorrelation and autocovariance functions are the functions of the time lag between T1 and T2, or the autocorrelation function and autocovariance functions are not depending on the time. Okay. So here if you let the time difference is tau, or time lag is tau, then the random process is said to be wide sense stationary random process if this condition is satisfied. Okay. The mean value must be constant and both autocorrelation and autocovariance functions are the functions of time lag tau. They are not depending on the time. So this is the one way of classification of the random process. Okay. So here we have two different type of random process: stationary random process and non-stationary random process. The statistical properties of the random process are not varying with time, then it is said to be stationary random process. Otherwise, it is a non-stationary random process. In the stationary random process, we have some more classifications. We have first order stationary, second order stationary, nth order stationary, or strict sense stationary random process. And another one is wide sense stationary random process. Here we can make a statement: if the random process is a stationary process, then it is a wide sense stationary also. But if the random process is wide sense stationary, that may not be stationary. All the stationary processes are wide sense stationary, and wide sense stationary process may not be strict sense stationary process, because here we are concentrating only on the two parameters, the mean and the correlation and covariance. There is the first and second order statistical averages. So this is a statistical averages mean value. The correlation and covariance are also called as the statistical averages. So this is the first order statistical average. This and this are called the second order statistical average. So that's why here the WSS process need not be strict and stationary random process. But if the random process is triplet random process, definitely it will be WSS random process. Understood this?